Today we're going to start talking about chapter 6. Chapter 6 is on normal distributions. So a normal distribution is just another name for a bell curve. And we've already started talking about bell curves before. We introduced bell curves in previous class. Bell curves are used so often by people in different fields. Different fields have adopted different terminologies for exactly the same thing. So bell curves are also called normal distributions. They're also called Gaussian distributions. So if you hear any of these, you know they're referring to the same thing, which is a bell curve. So let's review what we've talked about with bell curves in the past. We've said that there are some variables in real life that were distributed as bell curves. So what were some examples of those variables?
Height, weight.
Okay, excellent. Height, weight, IQ scores, standardized test scores. Good. So let's do an example of one of those variables. Let's say that we do weights of men. So again, let's say that we happen to go out in the population and we weigh a whole bunch of men, and we punch those weights in our calculator, and the calculator will give us the mean and the standard deviation. And let's say the mean is 180 pounds. And the standard deviation, which is approximately the average distance of each man's weight from the mean, is 20 pounds. And so let's say we plot that distribution, and we get a distribution that looks like this. So what this means is that there's some weight corresponding to the mean, or 180 pounds here, where the most number of men relatively have that weight. And as you move away from that particular weight in either direction, there's going to be less and less men having that weight. And so let's say that this is a probability distribution, where on the x-axis, you plot the weight. That's our variable of interest. And on the y-axis, we have a probability that that variable takes on each of its values on the x-axis. So the relative probability is the highest for this mean weight of 180 pounds. And as you move away from either direction, it tapers off and it's symmetric on both sides. So this is what we meant by when we said that this distribution looks like a bell curve. So in the past, we've also said that there's this relationship between the percentage of the population within certain values. So within, for example, one standard deviation of the mean, what are all the values that constitute one standard deviation within the mean? Between what and what weight? Yeah, because one standard deviation is 20 pounds, we can subtract and add one standard deviation from the mean. We get 160 pounds on the low end and 200 pounds on the high end. And all these values are within one standard deviation of the mean. And we also said that there was a percentage relationship for values in this range of being one standard deviation from the mean. So what percentage did that end up being? Yeah, 68%, right? And so on. As you go any number of standard deviations from the mean, there's a fixed percentage relationship for a bell curve. So this is all well and good. So again, let's do it. So within 2 standard deviations, that would be between what and what weight? 140 and 220. Yeah, 140 and 220. And in terms of the percentage of the men that have weights in that range, what percentage does that end up being? Yeah, Okay, and so on. And this is all well and good. If I were to ask you what percentage of men have weight between 160 and 200, that's 68%. Or what percentage of men have weights between 140 and 220, that's 95%. But you notice that the values in that range have a very particular structure, and they have to surround the mean, and they have to be the same distance away from the mean. So that's a very exact structure that you're requiring these values to be. So what if you wanted to know what percentage of men have weights in a much more arbitrary range, like for example, between 215 to 230, then based on what we've already talked about, you would not be able to answer that question. If you wanted to know what percentage of men have weights between 215 and 230, because values in that range are not surrounding the mean, and they're not the same distance around that. So today, we'll talk about how to answer that. We'll talk about, for any bell curve, how you can find the percentage of values within any arbitrary range of values. So let's build up to that. So the first question we're going to answer together is, let's try to find the probability that one random man's weight is less than 215 pounds. So the way that we're going to do this is we're first going to look at this data point, 215 pounds, and we're going to find the z-score of that data point. So in the past, we've talked about z-score. So what does it mean to find the z-score of this data point? Excellent. So the z-score of this data point is the number of standard deviations that this data point is away from the mean. So we're going to find z-score of 215. And basically we're finding the distance of this data point away from the mean, but measured in the number of standard deviations. So this is going to be 215 minus mean of 180. So that gives us a distance of 35 pounds. But that difference from the mean is in terms of pounds. Now we want that distance to be in terms of standard deviations. So then we would divide by the number of units, or the number of pounds in each one standard deviation. So then we would divide by 20. I'll just label this as 20 pounds per standard deviation. So this will give us the number of standard deviations for the mean. So this looks like 1 and 15/20ths, or 1 and, is it 3/5? 15/20ths, yeah, 3/4. So 1 and 15/20ths, yeah, 1 and 3/4, which is 1.75. Okay, so this is the z-score of this particular data point, 215 pounds from the mean. So once we get the z-score, let's talk about the second step. So it turns out that this bell curve has a very precise mathematical definition. And it's a very precise, it's a function, where basically you just plug in x, and this long mathematical expression will calculate into some value that describes the output of this function. So it turns out it has a very precise mathematical function. And so it turns out that those of you who have taken calculus, you know that there's an operation in calculus called the integral, where you can easily find the area under any function. So it turns out that the total area under this bell curve adds up to exactly 1. So even at these tail ends, where it goes on indefinitely and doesn't quite hit 0, but there's an asymptote at 0. If you take the total integral, or find the total area under this bell curve, from negative infinity to positive infinity, it adds up to 1, or it converges to 1. So that's very convenient for us, because we also know that if you add up all the possible probabilities in any probability distribution, then all those probabilities should add up to what? Yeah, so any probability distribution of any variable, if you add up all the probabilities, it should also add up to 1. So it turns out that now that we can make an equivalence between the area under a distribution and the total probability, because both add up to 1. So anytime we want to find a probability, then we can find an area under the distribution. So right now that might not seem like it's helpful, it might seem like it's more complicated, but we'll say that it's actually helpful to do that. So it turns out that you can find the area under any distribution by using calculus and finding the integral. In this class, we don't expect you to know calculus, but the point is that it's definitely possible to find any area using calculus. So there's a table that has been constructed for you. Somebody who does know calculus, or who has programmed the computer to do the calculus, has constructed a table where there's a relationship between z-score. For example, if we wanted to know this z-score here, so there's a relationship between that z-score and the total area under the bell curve to the left of that z-score. So there's a relationship between z-score and area to the left of that z-score. So using this table, if you know one quantity, you can easily find the other. If you know the z-score, you can find the area to the left of that z-score under the bell curve. And vice versa, if you know the area to the left of that z-score under the bell curve, you can find that z-score. So in this example, we happen to know the z-score. We know the z-score of 1.75. So we're going to use this table that I'm about to talk about and pass out. We're going to look up a z-score of 1.75, and we're going to find what area this corresponds to under the table. So I'm going to pass out these tables. So this is just taken from the textbook. First page is the main formulas for the class. And then if you flip the page, you'll see the next page says negative z-scores. And then the page on the back of that says positive z-scores. So let's talk about that particular page. So first of all, this z-score table is laid out as negative z-scores versus positive z-scores on the other side. So when do you think you would have a negative z-score versus a positive z-score?
Dependent on. I think it's less than the mean.
Okay, very good. So the z-score is dependent on the data point itself. And when we go to calculate the z-score, we take the data point, which is in this example 215, and we find the distance from the mean measured in the number of standard deviations. So you subtract the mean. So if you subtract the data point with the mean and you get a positive number, that means the data point is a value that's greater than the mean. If you take the data point, you subtract the mean, and it's a negative number, that means that data point was less than the mean's value. So in this case, we got a positive z-score. That means our data point was greater than the mean. And we saw that that was the case because the mean was 180 and the data point was 215. So the data point was greater in value to the mean. And that's why we got a positive z-score. So we're going to go to our z-score chart and go now to the positive z-score section. And we're looking for a z-score of 1.75. But the way that this table is laid out is in the very first column, we're gonna go up to 1 decimal place, so 1.7. And then we want 1.75, so we're gonna add on an extra 0.05. So then we're gonna look at the first row here in the table. And you see that that's labeled as 0.0, that means you're adding on an extra 0.0. And then 0.01, which means you're adding on an extra 0.01. But we wanna add on an extra 0.05, so we're gonna go over the 0.05. And then we're gonna take that row and then intersect it with the column that has just 1.7. And then whatever that number is, represents that area that we're looking for the z-score of 1.75. So what number do you see?
0.9599.
0.9599. Okay, everybody else getting that? Okay, good. Okay, so that's what this number represents, which is the area to the left of that z-score under the bell curve. So you look at this picture, this z-score that corresponds with a data point of 215, which is z-score 1.75, has a total area to the left of it, under the bell curve, of this 0.9599. So that would be the total area to the left. Here is 0.959. So that means that 95.99% of all the values of the population of men have weights that are less than 215 pounds. So that's going to be the answer to our question here, which is the probability that the weight is less than 215 pounds is going to be equal to the same area of 0.9599, because now we can make an equivalence to area with probability. Any questions? So we're going to make an equivalence with left area to the probability of being less than.
Yeah, how'd you find the left side of it?
And the left side of it was the number that we got from the table, which is 0.9599. So this number from the table represents the left area.
Yeah.
And that left area, now we can make an equivalence with the probability of being less than. And so this is the answer that we want. Any questions?
If the value was like 1.79, would we round up to 8 or would we still round down to 7?
Oh, 1.79, so if this had been 1.79, we can use our z-score table and look up 1.79 directly. Because this z-score table will go up to 2 decimal places. So we would go to 1.7 and then add an extra 0.09. So you would go over to the row that says 0.09. Any questions? Okay, so the table allows us to find any left area if we know it's the z-score. And then once we get the left area, we can find any probability of our variable being less than that number. Okay, so let's do another example. Let's say we wanted to find the probability that our weight was greater than 215 pounds. So generally the steps would be the same, which is take this reference point of 215 pounds, find its z-score, which we already did before, which is 1.75. Visualize a picture of this. So 215 is here, with a z-score of 1.75. But because we wanted to find a probability of the variable being greater than this reference number, greater than will be to the right, so this is equivalent to finding a right area. So before, we wanted to find the probability that the variable was less than the number, that was a left area that we were trying to find. And now we're trying to find the probability of being greater than the number, so that's gonna be a right area that we're trying to find. So, using this table of looking up the z-score, the number in the table gives us a left area, but now we want a right area, so how do you think we can find it?
Subtract from one.
Subtract from one, very good. So you know that the total area under the bell curve adds up to one. So this area that we're trying to find here is simply one minus this left area that we got from the table of 0.9599. So one minus that left area will give us this right area. So this right area will then be equivalent to this probability that we're trying to find of the variable being greater than this reference number. So what this means is the probability of a man's weight being more than 215 pounds is 0.04. That means 4% of the time a man will have a weight that is more than 215 pounds. Any questions? Okay, so now let's continue with the next related example. Okay, so let's say in the next example, we wanted to find the probability that our weight is going to be between two arbitrary values. So let's say between 215 pounds and 230 pounds. So if we were to visualize this to see which areas that we're trying to find to calculate this probability, then we're going to locate 200, so the mean is here, 180. So 215 pounds is going to be approximately this value, and 230 will be about this value. And then the probability of being between is the same as finding the probability under the bell curve, or finding the area under the bell curve between these two values. So this probability we're trying to find is the same as finding the area under the bell curve between these two values. So previously, we know how to find the area to the left of a value. And then just use the table, and we know how to find the area to the right of a value by using the table and subtracting from one. But now we're trying to find the area between two values. So based on what we talked about, how do you think we can use the table to do that? Yeah.
Well, first I would get what 215 is, and then I would subtract that from 1 to get everything like to the right, which would be like 215, and then I would get 230, and then the area below that, and then I would subtract that from the answer we had before.
Okay, very good. So that's definitely one way that you could do it. So when you do that, then basically you're taking this area to the right, and then you're removing this right area over here. So you're starting with this and you're removing this in order to get this middle area. And that's absolutely one way to do it. You can definitely get the right answer doing that. But if you do that, then that requires finding two right areas. And you notice that the table only gives us the left area. And we can definitely find a right area from a left area, but that involves an extra step. So how do you think we can maybe, instead of doing this an alternate way, that's maybe one less step, is to do what that involves just left areas?
Finding the 230 Z-score?
Yeah, so after you find the z-score, you can use the table to look up the left area, but how do you use the left areas directly to find the area that we want? Yeah.
You get the 230 area and you subtract the 215 area from it.
Okay, excellent. So basically the same idea, but now we're using left areas instead of right areas. So we're gonna basically find the total area to the left of 230. That'll be this. But that'll be the total area under the bell curve to the left of 230. That'll be this extra area that we don't need over here. We only want this middle area. So then we're gonna remove this area to the left of 215. So we find the top left area, and then we remove or subtract the bottom left area, and that'll give us the area in between here that we want under the bell curve. So that'll be our game plan. We're gonna find this what we want by finding the area between 230 pounds and 215 pounds. And we're gonna do that by taking the left area of 230 and removing the left area of 215. Okay, and each of these left areas, we know how to do from step one here. So we're just gonna calculate the z-score, look it up in the table to find the left area. It happens to be that we already know the second left area, the left area of 215 pounds. We already calculated that previously. So that was the 0.9599. So all we have to do now is find the first left area, which is the left area of 230 pounds. So how do we do that? Yeah, we're gonna find the z-score of this data point of 230 pounds, and we're gonna use that z-score in the table to look up the left area directly. So let's go ahead and calculate this z-score of 230 pounds. So if you haven't noticed, this is basically coming from a formula. It's x minus the mean divided by the standard deviation. So that'll be 230 minus the mean, which is 180, divided by the standard deviation of 20. And so that looks like
2.5.
Yeah, 50 divided by 20, which is 2.5. So the z-score is 2.5, and now we're going to use the table to look up that z-score and find the area.
0.9938.
Yep, 0.9938. So we're looking at 2.5, and then going over to the very first column, we're adding an extra 0, 0. So that's 0.9938. So this left area is 0.9938. And then we're gonna subtract these two to get this area in between that we want. So that looks like
0.0461.
0.0461.
Something different.
Wait, no, sorry, no, no.
Yeah, there should be a 9 at the end, right?
Yeah.
339, 0.339.
Yeah, 0.339. All right, so this is the final probability that is found by finding this area in between these two values under the bell curve. Yeah.
So where did you find the other area, the 0.9599?
Oh, that was from the previous step. that was from step one here. We found the z-score and then looked it up in the table.
Oh,
Yeah, that's from, an earlier question, where we found the probability that this weighs less than two.
so like, do you just use the formula and then go and look in the chart?
Yeah, so basically, if you repeat the same steps that we did, which is, find the z-score of 1.75, and then go to the chart, look at 1.75, you get the 0.9599. So that was this number here. Okay, any other questions? Okay, so that's finding, this probability of being in between these two values. So now you know how to find the probability between any two values for any bell curve. So let's go on to the next related question. So let's say that you wanted to find the weight for the man that is considered the heaviest 1%. So let's say we wanted to find the weight, find the man's weight. That represents the heaviest 1%. So if you draw a picture of that, there's some weight here that you're trying to find that's a heavy weight, that is the heaviest 1%. And what that means is that only 1% of men weigh more than that. Another way of saying that is that the probability of weighing more than this particular weight is only 1%. So that probability can be visualized with this area. So this area under the bell curve to the right, of whatever this weight is only 1%. So basically, in this example, there's this right area that you know that is 1%, and you're trying to find the corresponding data point. So this is different from what we did previously, where you knew the data point, like 215, and you were trying to find the area to the right of that. Now you know the area to the right of that, and you're trying to find the data point. So let's go ahead and review what we did previously, and then we'll address this case. So previously, we had X, a data point, like 215 pounds. And then we wanted to find the z-score. That was the next step. But how did we go from our data point X to the z-score? If you have a data point like 215, how do you convert that to a z-score?
We subtract the mean and divide by standard deviation.
Subtract the mean and divide by the standard deviation. So basically you use the z-score definition or the z-score formula, right? So there's a z-score formula here. X, subtract the mean, divide by the standard deviation. So that's how you go from X to the z-score. So then the next step was we went from a z-score to an area. And so how did we go from a z-score to an area?
You used the chart you gave us?
Yeah, use the chart. So we went from a z-score to a left area because the chart gives us only the left areas directly. So the means from which we go to from a z-score to a left area is we use the chart. And then If we're happy with the left area, then we stop. But if, let's say we wanted to find the right area, then we go one extra step. Then how do we go from a right area to left, or left area to right area?
Subtract one.
Yeah, subtract from one. So this equals one minus the left area. To get the right area. Okay, so this is a summary of the steps we took in the previous questions. But now in this question, instead of given a data point, that's what we're trying to find, we're actually given the right area. So in this case, we're gonna start here, and we have to land in the first step where we're trying to find the data point. So basically, we're driving exactly in reverse. So let's go ahead and basically go in reverse, step by step. Yep.
So should we add one to the right area now?
Okay, so let's go over it. So right now, we have a right area here of 1%. So the next step is to find a left area. So how do we find this left area then? We still subtract from one.
Oh, okay.
Because both quantities add up to one, right? So this is gonna be 99%. So now we have this left area here, so we're at this step. So now we're gonna go and find the z-score. So how do you think we can go from the left area to the z-score? By the same means as when we work in the forward direction by using the chart, so we're gonna continue to use the chart.
Look up 0.99.
Yeah, but this time, we use the chart differently, because previously, we started the first column and then worked our way to the middle to find the left area. But now, we're gonna start in the middle, that represents the left area, and find the number in the first column that represents the z-score. So, our left area needs to be 0.99, so we're gonna start in the middle of the table and look for the closest number to 0.99. And these numbers are sorted in order from left to right, top to bottom, so that'll help you find it. So find the closest number to 0.99.
2.33.
Okay, so what's the closest number itself to 0.99?
Oh, 0.9901.
Yeah, so good. So 0.9901 should be the closest number that you're seeing in the middle of the table that is closest to 0.99. You guys see that? Okay, so then that 0.9901, what z-score corresponds to that left area? Yeah, so it should be 2.33. So z-score of 2.3 and then add an extra 0.03 should give you that left area point of 0.9901. Everybody find it okay? So again, if you look at a z-score of 2.3 and then add on an extra 0.03, so go to 2.3, add on an extra 0.03, you should see that left area of 0.9901. So the z-score that has a left area closest to 0.99 is going to be a z-score of 2.33. So this step's very important. So if you not exactly clear on how to find it, feel free to let me know and I'll work around or ask your neighbor. Yeah. Oh, we're just trying to find the left area that's closest to 0.99 because there's no left area that's exactly 0.99. Yeah. Anybody else? Okay, so now that we found a z-score of 2.33, now we're here. And we just need to find our original data point that represents a weight. So before, there was a z-score formula we used, and now we use the same z-score formula, but we plug in what we know and we solve for what we don't know in that formula. So in the z-score formula, it was, so in this case, we know the z-score, that's the 2.33. x, we don't know, that's what we're trying to find. The mean we know, that's given as, I erased it previously, but the mean was given as 180, and the standard deviation was 20. So the mean here will be 180, standard deviation is 20. And then all we have to do is solve for x. So if we brush off the rust from our college algebra and solve for x, what's the next step to getting closer to isolating x? So what do we do to both sides of the equation?
Multiply them by 20.
Yeah, multiply both sides of the equation by 20. So then that'll be 2.33 times 20 on both sides of the equation. We'll cancel out the divided by 20 on the right. So then we'll get x minus 180. And then now we have to do what to get rid of the minus 180? X, yeah, add 180 to both sides of the equation. So then we'll get x is 2.33 times 20 plus 180. So if you plug that in, what do you get? What is it?
226.6.
226.6. Everybody else getting it? This will be in pounds. So that means the man's weight that represents the heaviest 1% is going to be 226.6 pounds. Only 1% of men weigh more than that. So this question that phrased the heaviest 1%, what percentile is that? Okay, excellent. So this is the same as saying the 99th percentile, because this data point is greater than 99% of all the values. So this is the 99th percentile. So now you know the 99th percentile is the same as the area to the left under the distribution. Okay, so let's move on. Oh, before we do that, so this data point of x that we finally got from the z-score, we basically started with the z-score formula, plugged in what we knew, and solved for x. That's one way we definitely could have done it. So the second way, maybe the more intuitive way that you could have done it, is we know the z-score of our data point of interest ends up being 2.33. So what that means is that whatever this weight is, it is 2.33 standard deviations away from the mean, because that's what a z-score means. So a z-score of 2.33 means that this data point is 2.33 standard deviations away from the mean. So to get that value, we would start at the mean of 180, and then we would add on 2.33 standard deviations, where each one standard deviation is 20 pounds. So then we would multiply this by 20, and this is the same expression that we would get if we were to just manipulate this z-score formula using algebra. So it's the same expression at the end. So you can think of it as a z-score as the number of standard deviations from the mean. So you start at the mean, and then add on this number of standard deviations, multiplied by this number of pounds for each one standard deviation. Any questions? All right. So moving on. So previously, we found the probability that a variable is less than a number. For example, that the weight is less than 215 pounds. That was just finding an area to the left of the bell curve. We also find the probability that a variable was greater than the number. That was finding the area to the right under the bell curve. But we haven't done this case. So let's say we wanted to find the probability that a random man's weight that we select is equal to 215 pounds. So the way that we approached this type of question previously was that we converted this probability into an area, and we found that area. So the previous question ended up being a right area under the bell curve, or left area under the bell curve, for less than. The next question ended up being a right area of that data point under the bell curve. So in this case, it ends up being, relative to 215, it ends up being the area under the bell curve of that point. So what do you think that area ends up being?
0.
Yeah, so that area ends up being 0. So the reason being, area is designed to measure the space inside a region. But this, this line here has no area within it. So this, the area of that line under this bell curve is going to be 0. And so this should feel really weird, because this is supposed to represent the probability of a random man's weight being equal to 215 pounds. So this is kind of suggesting that this is impossible, because this probability is 0, because the area is 0. So who can reconcile this and try to make sense of why this probability of observing a man weighing 215 pounds, why would that be 0? Yeah.
Because there's like, it's just one specific weight, it doesn't count for like 0.000000. Like, you could weigh 215, but you're probably 215 point something.
Okay, excellent. That's exactly right. So when we ask this question of the probability of a weight being 215 pounds, what we're implying, because this is what we call a continuous distribution. So you had to have some homework on distinguishing between a continuous distribution and a discrete distribution. And at the time, we hadn't talked about this yet, because it wasn't relevant yet. But now it's relevant, so let's talk about it. So a continuous distribution means that any probability, so the probability of any value in a certain range is considered possible. So when because we're talking about weights here, weights is a continuous distribution because you can have a weight that is 180.1 pounds. You can have a weight that is 180.23 pounds, and so on. You can have any weight within a certain range. So we can contrast this to another type of distribution that we call a discrete distribution. So a discrete distribution, for example, if you're looking at points in a basketball game. So if you label this x-axis to reflect the points in a basketball game, then you might see a distribution that looks like this. Where you see where this y-axis is the probability of each of these points occurring. So why do you think you see all these gaps in this particular probability distribution that represents points in a basketball game?
Because you can't get half points.
Yeah, very good. You can only get 0 points or 1 point. Those have probabilities. But half points, that's impossible to happen, so the probability is 0. So that's why you're seeing these gaps where the probabilities are 0. But in a continuous distribution, you don't have gaps because the probabilities are theoretically possible. You can have weights that aren't just whole numbers. You can have any decimal numbers that are possible for weights. So that's why you have this continuous distribution for weights. So given this continuous distribution for weights, if you're to be asked what's the probability that that particular weight is 215 pounds, that implies that it's exactly 215 followed by an infinite number of zeros. It's 215.00000 and so forth. Because this is a continuous distribution of weights and you're allowed, any weight is technically allowed. And so this probability of being 215 with an infinite number of zeros at the end is defined to be a probability of 0. But in real life, when you say that somebody weighs 215 pounds, you're actually giving it a tolerance. In real life, weighing 215 pounds is really between 214.5 approximately to 215.49, for example. So in real life, when you say that you weigh 215 pounds, it's really this range of possible weights. And so when you have this range, you can definitely find the area of that range under the bell curve, and it's a non-zero probability. So mathematically, in a continuous distribution, the probability of a variable being an exact value is defined to be 0 for a continuous distribution. But in real life, even with that continuous distribution, that value is actually a range of possible values in which you actually have a non-zero probability. Any questions? So if you're to be asked what's the probability that this variable in this continuous distribution is equal to this number exactly, then that's going to be 0. Okay, any questions? So previously, we found this probability. That was the very first question we did. We calculated the z-score, we looked it up in the table, and we got 0.9599. But let's say that I were to ask you what's the probability that a weight is less than or equal to 215 pounds. So compared to the previous answer of 0.9599, do you think it should be the same or less than or greater than? So the difference is, the previous one was strictly less than, but now we're including the 215 pounds as well.
Should be the
Same, yeah.
It should be the same,
Should be the same way.
because since the comparative probability of it being exactly 215 is 0, it should not affect the lesser than probability in a meaningful way.
Okay, excellent. So it should be the same, and the reason for that is that we just said that the probability of a weight being exactly equal to 215 is 0, and the only difference between these two probabilities is that we're including this extra one data point of 215. But the probability of that one data point exactly happening is 0, so now we're adding on an extra probability of 0 onto there, which is 0, and adding on an extra probability of 215, which is 0, and so it ends up being exactly the same number. So the significance of that is when you're talking about continuous variables and you're writing out the probability, you can be a little loose in whether you want to include that boundary point or not. It really doesn't matter whether you include this boundary point of 215 or not, because in a continuous distribution, these two probabilities will end up equaling each other. Any questions? Okay, so I emphasize continuous distribution like weights because if you were to look back in the example of the discrete distribution, like a basketball game, if I said, what's the probability of getting 0 points or 1 point or 2 points in the game, what would you do to try to find this probability?
You'd have to find the mean first, right?
Well, you already have this distribution drawn for you where you have the heights of each of these bars, and the heights represent the probabilities. So how would you find the probability of either getting 0 points, or 1 point, or 2 points in this basketball game?
You would just add up the heights of the bars, right?
Yep, so probability with or is the addition rule, right? So that means that you can add up these separate probabilities. So you add up the separate probabilities or the separate heights of the bars. So you would add up the height at 0, the height at 1, or the height at 2, and that would represent the total probability. Now, and this is only for a discrete distribution where you can add up the heights of the bars. For a continuous distribution, which we just did, you can't add up the heights of these bars because it's continuous and there's an infinite number of bars. So instead, you have to find the area. So in a continuous distribution, to find probability, you find area. In a discrete distribution, to find probability, you add up the heights of the individual bars. Okay, any questions? So before, like we said, in a continuous distribution like weights, there is really no difference in value between these two. If you wanted to find the probability that a weight was strictly less than 215, or the probability that the weight was strictly less than and also included 215, then because you're including a 0 value in there for the probability, then it ends up being exactly the same probability. So adding this extra 215 pounds doesn't matter in a continuous distribution. But in a discrete distribution, does it matter? If you were to say, I want the probability of less than 2 points versus less than or equal to 2 points, is that different? So in one case, it's strictly less than 2 points, which is just 0 or 1. In the other case, it's less than or equal to 2 points, which means you're including the 2 in there as a possibility. So in this case, can you ignore are these two probabilities the same?
No.
Yeah, no, because in one case, you're just adding the heights of the bars between 0 and 1, which is strictly less than 2. And in the other case, you're adding the height of this bar at 2 as well. So because in a discrete distribution, you're adding the heights of all the bars, you have to include any height of a bar that, of a data point that you're considering. So in this case, because you're considering a 2 in there as well, you have to add in the height of that bar as well. So these probabilities are different. So that's why when you're finding probabilities, it matters whether the distribution is continuous, like weights here, or discrete, like points in a basketball game. So if it's a continuous distribution, you find probabilities by finding area, and that's what the z-score chart allows us to do. And versus if you're finding the probability of a discrete distribution, you're adding up the individual probabilities or the heights of the individual bars.